Hi, this is the video presentation of the tool paper ConCert, testing, verifying and extracting smart contracts. So smart contracts are distributed applications running on a blockchain and are typically used for sensitive transactions in a financial or legislative setting. By design, once smart contracts are deployed on the blockchain, they're impossible to change. And there have been numerous attacks on smart contracts, resulting in major monetary losses, such as the DAO attack, where $15 million worth of Ether was lost, and the attack on the Uniswap, where 99.5% of the funds were lost initially. In context of this, it's clear that ensuring correctness is imperative, and that's the aim of ConCert. So ConCert is a COG framework for testing and verifying smart contracts, and it's developed at Aarhus University at the Department of Computer Science. It features verified extraction or translation to real-world smart contract languages like Liquidity and Cameligo and Concordium's Rust framework. In the figure we see ConCert's pipeline. In ConCert, smart contracts are COG functions, and we connect a verified execution layer that models smart contract execution, which allows us for proving temporal properties about smart contracts. And we develop a QuickCheck based property-based testing framework that connects to the execution layer, which allows us to test not just functional properties of contracts, but also properties on entire execution chains. And once tested and or verified, contracts can be extracted in a verified way to various smart contract languages. And here the trusted computing base of the extraction pipeline is very small and relies only on pretty printing from a generic lambda calculus-like language to the target languages, so Liquidity, Cameligo, and Rust. We won't focus on the extraction part here in this presentation. We'll focus mostly on the property-based testing framework. So property-based testing is a testing technique that uses randomly generated test inputs to test properties on code. And this approach can be effective at discovering bugs, since thousands of test cases can be executed automatically, and usually in a very short amount of time. The COG Proof Assistant has the QuickCheck library for property-based testing, and we connect the execution layer to QuickCheck. So contracts in ConCert uses the common message passing paradigm, where contracts send and receive messages and update their states accordingly. The property-based testing framework in ConCert relies on generating pseudo-random messages and then populating blockchain execution traces with these messages. Then these generated execution traces are then used for testing functional or temporal properties of smart contracts. See the paper for more details on how this works. So here we show an example of how to test safety properties on the reference implementation of the ERC20 token contract in ConCert. So ERC20 tokens is the backbone of many smart contracts, and the specification states that they must have at least 3 endpoints: transfer, approve, and transfer from. Transfer obviously transfers tokens from one account to the other. Approve approves one account to transfer on the behalf of another account, and transfer from transfers on behalf of another account. And in ConCert we represent this with the message type shown here, which is a type with 3 constructors, one for each endpoint. So in order to test a contract with this message type, we must be able to generate pseudo-random values of this type. Luckily, QuickCheck provides various mechanisms to make this process mostly automated. And so here's an example of how to test a simple safety property of the transfer endpoint in ConCert. Here we use a Hor triple-like notation, where in the first bracket is the precondition, and this precondition states that the incoming message is a transfer, and the post condition is some predicate on the contract state before and after the transfer, and in this case the predicate could be it could assert that the balances are updated correctly for the sender and the receiver. And this is tested using QuickCheck, where by default thousands of tests are executed, and it usually takes less than a minute. We've performed several case studies with ConCert's testing framework to determine its effectiveness at finding real-world bugs. For example, we've been able to rediscover a known bug in any ERC20 compliant token, which involves a very particular ordering of the transfer from and the proof endpoints. We've replicated the reentrancy attack on the Uniswap protocol, and similarly for the infamous reentrancy attack on the DAO, which is an e-voting contract. We've also rediscovered a token duplication bug in the iToken contract, and in the paper we also show how we find a pricing bug in the Dexter token exchange contract that would allow for arbitrary profit from token exchanges. And this shows that our approach to testing smart contracts is not only capable but also effective at finding bugs in real-world smart contracts. So in conclusion, we've presented ConCert, a framework in the CoC proof assistant for testing, verifying, and extracting smart contracts. We've shown that the testing framework is effective at discovering bugs. And in conjunction with the extraction pipeline, which we've not presented here, this gives us a high insurance pipeline for smart contract development and extraction to real-world smart contract languages.